This section deals with chemical equations and chemical reactions. Every chemical reaction must be represented in some way in shorthand, and the way we represent them is using what is called a chemical equation. A chemical equation is very similar to a mathematical equation in that it has two sides. The difference is, instead of having an equal sign, we have an arrow into place. And what the arrow shows is directionality. The arrow in a chemical equation shows you what direction the reaction is proceeding. It shows you that it is going from the left to the right. Most of the time, that is the case. Throughout the course, you're going to see different arrows in there. You might see double arrows. You might see the arrow pointing back to the direction, but the arrows show what's happening. The other important aspect is what we have to begin with and what we have to end with. The things we are beginning with are called the reactants. They are the things that you are reacting together, as the name entails. The things on the right side of the arrow are called the products. I'll write that neatly. Products, because they are the things that are being produced as a result of a chemical reaction. One thing we know for sure is, just like in a mathematical equation, all things on both sides of the equation must be equal. So the reactants and the products have to be the same number. What do I mean by that is that when I count up the atoms on the left side and I count up the atoms on the right side, I have to have the same number of each component. The only way we can fix that is to change the coefficient in front. The number in front, again, just like a math equation, is called a coefficient. Coefficients are changeable, but the small numbers, called subscripts, are never changeable. The reason why we can never change those is because when we're writing our formulas, for example, when we wrote the formula for hydrogen and oxygen when they're together, we learned that H is plus, O is minus 2. So the formula formed H2O was a result of that combination. Therefore, that is always the ratio they will combine. Therefore, we can never change the subscripts. All right, so again, as we got balancing equation, the law of conservation of mass says that matter can be neither created nor destroyed. Therefore, all chemical equations must be balanced by placing coefficients in front of the terms in a reaction. Again, the subscripts never be changed. In all, in the end, the elements must be equal on both sides of the equation. Let's look at some examples of how we do this. The good thing and bad things about balancing equations are that in balancing equations, you will always 100% know if you're right at the end, because if things are equal on both sides, then you know that you have a balanced equation. If things aren't equal, then you do not have a balanced equation. The bad thing about it is there's no steps. There's no one way to do it. It's sort of like a puzzle where you sort of just have to work it out sometimes. Some are easier than others, but it takes some time. All right, let's look at examples. When you balance equations, you start by looking one element at a time. And what I generally do is I start on the left and I compare left and right. So for example, when I'm starting, I notice that I have potassium here. I have potassium on the other side of the equation. When I say the other side, I'm talking about the other side of the arrow. Right? The arrow divides the equation in half. So on the left side, I have 1 potassium. On the right side, I have 1 potassium. So they are already balanced. Chlorine comes next. On the left side, I have 1. On the right side, I have 1. So they are already balanced. Next, I move to the oxygen. On the left, I have 3 oxygens. On the right, I have 2 oxygens. In this situation, there is no number I can multiply by here that would give me 3. We must multiply by whole numbers. Now, one theory says you can multiply by fractions and reduce, but that's not one way I do it. And in the book, they show examples of doing that if you are interested in looking and seeing how to do those. What I always choose to do is I look at those two and say, since they are both have to be changed, the least common multiple of 2 and 3 is 6. Therefore, I need to get 6 oxygens on both sides. To do that on this side, I put a 3. To do that on this side, I put a 2. So now my oxygens are balanced with 6 on each side. In doing so, I now have also changed potassium and chlorine, but that is okay because they can be fixed as well. On the left side, I now have 2 times 1 potassium and 2 times 1 chlorine. When a number is in front, it distributes through to everything that is there. Therefore, I have 2 potassiums and 2 chlorines on the left and only 1 on the right. Again, I can fix that by putting a 2 there. When you are finished, balancing equations, I will always ask that off to the right, you write the coefficients down for the balanced equation. So off to the side, on some of the problems you'll be given, I'll ask you to do this: 2, 2, 3. It is just a shorthand representation so that you can very quickly check them. I can very quickly check them, and when we're discussing those in class, we can look at how it balances without going through the whole equation. Our next example is a type of reaction. C2H6 plus O2 produces CO2 and H2O. Again, one step at a time. Carbon, I have 2 on the left, I have 1 on the right, so I put 2 on the right. Hydrogen, I have 6 on the left, I have 2 on the right, so I come over here and put 3 here. Oxygen is our next item. I have 2 oxygens here. On the other side, I have oxygen occurring in 2 places. When you have oxygen occurring in 2 places, you have to add it up all occurrences. So I have 2 times 2, which is 4 here, and I have 3 times 1, which is 3 here, giving me a total of 7 oxygens on that side. The problem with having 7 oxygens is that there's nothing I can multiply by here to make that equal to 7. So I look back and I say, what's giving me the problem? And the problem is arising from the fact that this side is always going to have to be an even number of oxygens. This is always going to give me an even number, but this one is not. I am going to get an odd number if I multiply by an odd. So what I do is I simply say, let's try an even number. And if I go to the next thing, I know it's going to be some multiple of 3. Well, let's try the next highest multiple of 3, which is an even number, 6. So now I have 6 oxygens there. Let's go back and do the hydrogens. I have 6 hydrogens over here. 6 times 2, 12. So I'll put a 2 here now. Double that. I have 2 times 2 carbons, which is 4. So I'm going to come back here and fix this and make a 4. So I have 4 carbons there. Now, let's go back to the oxygens finally again. On the right side, I have 4 times 2, which is 8. 6 times 1, which is 6. 8 plus 6 is 14 oxygens. On the left side, to get 14 oxygens, I need to simply multiply by a 7. So again, I told you when you're done, you can always double check. So I always encourage you to do that. I do it this way. 2 times 2, 4 carbons. 4 times 1, 4 carbons. 2 times 6, 12 hydrogens. 6 times 2, 12 hydrogens. 7 times 2 is 14 oxygens. On the right, 4 times 2 is 8, plus 6 times 1 is 6, is total of 14 oxygens. So that equation is balanced. Off to the side, I would write 2, 7, 4, 6. In our last example, you'll notice that we have polyatomic ions. Polyatomic ions, when they're involved, and they're on both sides of the equation, I always encourage you to keep them together and count them as one thing. It will save you an immense amount of time. For example, you'll notice that we have nitrate on the left side and we have nitrate on the right side. The only time we do not do this is if you do not see on that form on the other side. So for example, in some reactions you might see nitrate on this side, but there's no nitrate in the product side. When that happens, then you do have to split it up by nitrogen and oxygen. But until that happens, if you can, keep them together. So when I'm balancing this equation, I have 1 calcium here, 1 calcium here. I have 1 nitrate here. Actually, I realized I have a typo there. It should be 2 there, so I have 2 nitrates there, so I need to put a 2 here to make 2 nitrates. Sodium, I have 1 here. I have 2 here now, so I can come back to this side and put a 2. Hydroxides, I now have 2 times 1, which is 2, and over here I have hydroxide in parentheses 2 outside, so I have 2. So my numbers are 1, 2, 1, 2. Balancing equations is essential. A lot of the work we do from here forward and a lot of the mathematical calculations we do are based on having a balanced equation. Everything in this course builds. We learned in Chapter 2 how you write chemical formulas. We learned that if you didn't put them together right, you don't do things. Now in this chapter, we're learning how you write equations and what do you do to write equations. So if you don't put the equations together correctly, then or balance them correctly, then you cannot proceed from there. And as we go on, we'll look at more how they relate to other things we do. Just spent time talking about how you balance equations and the importance of balancing equations. What we're going to look at now is how you identify the different types of reactions. And identifying types of reactions is a key and crucial element in being able to predict and write an equation for a reaction that may happen when you're only given the reactants. So understanding the patterns of reactivity show us a lot about what's going to happen. And there are 5 types of general reactions we're going to look at here. The first type of reaction is called a combination reaction. It's also called a synthesis reaction. Synthesis reactions or combination reactions are when you have 2 or more substances on the reactant side or the left side of the equation mixing together to produce one product. Okay, so again, the way I always remember that is combination. You're combining some things to make one thing. And an example here is like we would have done earlier on. I take 2 elements, magnesium and chlorine, combined together, they produce magnesium chloride. Now again, these are pretty simple to do prediction-wise. If you're given just 2 elements and you're asked to write the products out of that, you simply do as we've done earlier. You look up the charge of the 2 elements, and then you do the crossover method and write the formula. So a combination reaction, again, 2 reactants forming one product. The next kind of reaction is sort of the opposite of that, and it is a decomposition reaction. A decomposition reaction is a reaction in which there's one reactant. So on the left side of the arrow, there's only one substance there. And on the right side of the arrow, it's decomposing or breaking down, we know what decomposition means, into 2 or more substances. Now those 2 or more substances can be elements, compounds, or any mixture of those 2. Decomposition reactions are the only types of reactions that I will not expect you to be able to do throughout the course of this year. Decomposition, based on what you know and what you learn throughout this year, it is difficult for you to learn what things will break down to and what they will not. So for a decomposition reaction, if I'm asking you to write an equation for it, I will give you all components and you simply have to be able to write it out based on the names. The next type of reaction is called a combustion reaction. A combustion reaction is pretty much as the name says. Something combusts in the air. When we hear the word combustion, we talk about things burning. In general, combustion reactions are when you have a hydrocarbon. Hydrocarbons are identifiable because you have a compound that has carbon and hydrogen as your main ingredients. So the first 2 things in the formula will be carbon and hydrogen. In a combustion reaction, a hydrocarbon will always react with O2. Oxygen is present and is needed in the air for something to burn. And the products are always the same. So these are easy to identify because you will always produce water and carbon dioxide. Now, if the hydrocarbon has something else in it, like nitrogen or sulfur, then you would also produce sulfur dioxide or nitrogen dioxide as well. But in most cases, you'll just have a plain hydrocarbon reacting with oxygen to produce water and carbon dioxide. Always, 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 when you see those things being produced from those 2 types of reactants. And the key is, these can be produced from other types of reactions as well, but when you have a hydrocarbon and you have oxygen reacting, then you know you have a combustion reaction. The next type of reaction is one of the most common types, and it's called a single replacement reaction. A single replacement or single displacement, as it's referred to, either way is fine, is when you have a single element reacting with a compound, and as a result, they produce a new compound and a different element. A key expression we have to remember here is that likes replace likes, and that component comes in important here when we start predicting reactants and start predicting products out of reactants. In our first example, we have sodium reacting with copper chloride. Since sodium is a metal, it will replace its like component in the compound. So sodium will replace the copper, sending the copper out by itself, and then the sodium joins up with chlorine on the other side. Now you'll notice that chlorine on the left side has a 2 with it, but on the right side only has a 1. That's because of what it's joined up with. On the left side, or the reactant side, we have chlorine with copper, and copper was +2, and chlorine was -1, so in that case I needed 2 chlorines. But in the product side, chlorine is matched up with sodium, and since sodium only has a +1 charge, I only need 1 chlorine. This is why we need to balance equations, because when things switch, they don't necessarily combine in the same ratios. All right, so that's a single displacement reaction. Single element replaces part of the compound to form a new compound and a new single element. I always use the example of a boyfriend and a girlfriend together. That's our copper and our chlorine. It's a couple together. And the little sodium is sitting out here all along, and he's a friend there. So little Sammy Sodium walks up to little Carl Copper's girlfriend, Clara Chlorine, and says, you know, I think I'm going to take her. So as a result, after the breakup, Sammy and Clara are together, and little Carl Copper's left alone by himself. So it's a single displacement reaction. Now, single displacement reactions can also happen with a non-metal in place. In our example here, we have fluorine gas reacting with sodium chloride. Now, since fluorine is a non-metal, it will not replace the sodium. It will not join up with the chlorine on the other side and leave sodium by itself. That can't happen because they are both negatively charged. Just like above, sodium couldn't join up with copper on the other side and leave chlorine by itself because they're both positively charged. Positive charges will repel one another. Opposites attract, likes repel. You should have learned that in physics. So therefore, sodium has to join up with chlorine on the other side. Just as in this case, fluorine tends to form negative ions. So when fluorine forms an ion, it has to join up with sodium. So since it's a non-metal, it will replace the non-metal chlorine and it will join up with sodium to make sodium fluoride. Chlorine then will go off by itself. Now again, since chlorine's by itself, we learned about diatomic molecules. Chlorine, when it's written by itself, just the same as fluorine when it's written by itself, has to be written as Cl2 and F2 because they are diatomic. In nature, when they're by themselves, we said that they will always exist in pairs. They cannot exist alone. The last type of reaction we look at is called a double displacement, and it's very similar to the one above, except you have two compounds reacting together, and they will switch partners to form a new compound. In other words, we have two cations, which are the positive ions. Remember, cation stands for you see a positive ion. Will switch places with one another. So calcium is together with chlorine, sodium is together with oxygen, hydroxide. As a result of the reaction, calcium comes over with hydroxide to form calcium hydroxide. Calcium's +2, hydroxide's -1, so we have to refigure out the charges and rebalance those charges. That's why we need parentheses with the 2 there. Don't just jump to conclusions and say CaOH. Sodium will switch and go with chlorine. Sodium is +1, chlorine's -1, so we'll have NaCl on the other side. So we have two partners switching places. Calcium goes with hydroxide, sodium goes with chlorine. These 5 types of reactions are key. Identifying what is happening by looking at reactants will allow us, as we move forward, to predict reactions. By simply knowing what's reacting together, we should be able to predict what's going to form out of it. And that's a major part of this class, is being able to do that, which we'll be talking about in the upcoming section. We just talked about how you identify types of reactions, and now we're going to put into action how you use those identifications by looking at reactants and understanding a set of reactants, what's going to happen out of that based on what you see. Again, to recap, we talked about the 5 types of reactions that exist. They are a combination, which is 2 elements combining to make one product. A decomposition is one product or one reactant breaking down into 2 or more products. A single replacement is when you have a single element reacting with a compound to form a new single element, a new compound. A combustion reaction is when you have a hydrocarbon reacting with oxygen. They will always produce carbon dioxide and water. And then finally, a double displacement is when you have 2 compounds reacting together and they end up switching partners. So the key, again, to writing equations is being able to identify what you have. So here are some examples that are not in your notes and need to be put in your notes of some problems like you would see, and you would need to be able to predict what kind of products are going to form out of that. In our first example, we have iron reacting with oxygen. My first thing I have to do is identify what kind of reaction is that. Well, since I see 2 elements reacting together, I know I have a combination. What happens in a combination is those 2 things combine to make one thing. So I know I'm going to take iron and oxygen, combine them into one compound. So what I'll do is I'll say, all right, iron is +3. I know that by looking at the periodic table, looking at the charge for iron. Since I'm not given a specific charge, I'm going to assume the one that is most common, and we taught you how to do that. Oxygen is -2. So when they combine, Fe +3 is going to combine with O -2 to form Fe2O3. O3. We would then need to balance that equation as we learned earlier. But for the sake of time here, I'm simply just writing the equations and assuming you can balance. In our next example, we have an element, oxygen, reacting with a compound, magnesium chloride, MgCl2. When I have an element with a compound, that is a single displacement reaction. Since oxygen is a non-metal, we need to see that it will replace part of that compound. Oxygen is a non-metal, so it will replace the non-metal portion of the compound, which is the chlorine. So magnesium is +2, is going to go with oxygen, which is -2, to form MgO. Chlorine, which was part of the compound, is now going to go off by itself. And since chlorine is one of the 7 diatomics, I've got to remember those 7. And since I'm writing chlorine that way, it has to be Cl2. Once again, you would have to balance this equation, but for the sake of right now, we're going to leave it at that. For example, CH4 reacts with O2. CH4 is a compound reacting with an element. You might be very tempted to say, oh, this is a single replacement reaction, and go from there. But remember, when the compound is a hydrocarbon, meaning carbon and hydrogen is the main components, you are looking at a combustion reaction, not a single replacement. So our combustion reaction always produces the same 2 things. Without any thought, we can say CO2 and H2O. In our next example, we have magnesium and nitric acid. Element, compound. Once again, element, compound is going to be a single displacement. Magnesium, since it's a metal, tends to form positive ions, so it's going to replace the cation of the compound. In this case, the cation of the compound is the hydrogen. So magnesium is going to go with the nitrate. Magnesium is +2, NO3 is -1, so they're going to form MgNO3 2. And I do highly recommend you doing this off to the side somewhere so you can sort of keep track when you're rewriting stuff. It sort of helps make things easier until you get a better hang of it. And then the other component then is going to be the hydrogen going off by itself. And if I wrote it that way, I'd be incorrect, because hydrogen is diatomic. I need to have the 2 there. My next example has a compound and another compound. When you have 2 compounds, instantly you know you have a double displacement. So what's going to happen in a double displacement? Iron is going to join with chlorine, hydrogen is going to join with sulfur. In this case, iron already has a charge, so we'll need to maintain its charge. You're not going to look up the chart and see what it is. Iron in this case is +2, and I know that because sulfur is always -2. Therefore, to balance that, iron has to be +2, and since there's only one iron, I knew that that had to be +2. So iron is +2. It's going to go with chlorine on the other side, which is -1, to form FeCl2. Hydrogen is +1. It's going to react with sulfur on the other side, which is -2, and it's going to form H2S. All right, so predicting equations is important, being able to do that. Now, another important part is being able to take the words, which a lot of times you'll see equations written as, and put them into formula or equation format. So in a problem or a word in a book or a text might say potassium reacts with fluorine, I have to be able to take and put that into chemical equation form. So I simply write it as I see it. Potassium, that's K. The words reacts with means plus. Fluorine, F2. In looking at that, think about it a second. What kind of reaction is that of the 5? If you said combination, you are correct. Potassium reacts with fluorine. K is +1, F is -1, so it will form KF. Now again, don't just automatically bring that 2 over here and make it KF2, because that 2 is there on the reactant side because fluorine is diatomic. But when fluorine reacts, it takes a charge of -1, and the subscript will be based on whatever it would need, depending on what it reacted with. Our next example, iron 3 hydroxide reacts with phosphoric acid. All right, so iron 3 is Fe +3. Hydroxide is OH -1. Remember what we said earlier, if you see no prefixes, you have to use charges. So Fe plus 3 and OH minus 1 is going to form Fe OH in parentheses 3 reacts with, so I put my plus sign, phosphoric acid. It's an acid, so automatically the first part's H, which is plus 1. Phosphoric, because it ends in ic, that means it originally came from 8. So phosphate is PO4, and that's negative 3. So H plus 1, PO4 minus 3 off the side, the little scratch work, and I get H3PO4. All right, there's my reactants. Now, I'll give you a second to think about it. What kind of reaction is this? It is a double displacement. Hopefully you identified that correctly. And as a result of the double displacement reaction, we have Fe going with phosphate. So in this case, Fe was plus 3. It's going to go with the phosphate, which was minus 3. So Fe plus 3, PO4 minus 3 are going together. So since it's opposite charges, I can just put that together to Fe PO4. Remember, the cation always gets written first in the formula. H is going to go with OH. H is plus 1. OH is minus 1 to form HOH. Now, HOH, you need to train yourself, that we'll see that a lot. HOH is the same as H2O. So when you have that, you should always write it as H2O. I'd like you to try this reaction on your own, and you can pause the tape right now and see if you can do it. And then whenever you continue, you can, when you're finished, you can hit continue the recording and you can see how I do it. You have completed the problem. Now let's take a look at it. Cu, copper, reacts with nickel 2 acetate. Well, nickel 2 is Ni, that's plus 2. Acetate is C2H3O2, that's minus 1 from your polyatomic ion list. So that's Ni, parentheses, C2H3O2, parentheses, 2. And I look at it and I say that is a single replacement. Copper is going to replace the nickel. So copper is going to join up with nickel. Copper's most common charge is plus 2, I believe. Yes, it is plus 2. So copper is plus 2. Acetate is minus 1, so I'm going to have the CuC2H3O2, 2. And then the nickel is going to go off by itself. And a single replacement.